Okay, yeah, it's recording now. So, hello everyone. Today I'll be presenting this paper on multimodal few-shot learning with frozen language model. This is a pretty small paper, so and like there are few concepts which are already known, but I'll try to cover as much as I can. And please feel free to stop me whenever you have any questions or anything, so that I can clear it out, or so that we can have a good discussion as well. So. So we'll be covering, so first I'll be giving you guys like a high level summary of what exactly this paper is about before we even go into depth of this paper. Then I'll give you the introduction of from where are they coming, where are they coming about for this paper. And then we'll be talking about the training, the experiments, and a few results and observations and after that we'll be concluding the paper. So going ahead, the high level summary of this paper is basically is that they have they have a language model which is, let's say in this case they can use GPT-3 or GPT-2, and they which has already been trained on a large number of text data, basically any text which is present in internet, let's say Wikipedia, Reddit, or anything. And so they are basically freezing the parameters of the language model, and they're mapping them to the token of the vision encoder that has the vector representation, and then they are making it do tasks like vision questioning, answering, and few shot image classification. So go if you look at the left hand side image, for example, this face, this person looks like happy. The emoticon is happy. The second person is sad, and then the third person, this person is like what? So they are prompting. The prompt is this person is like what, and then they're giving like a scared emoticon, dot, and end of sentence. So, and for example, even in the third example, with one of these, I can drive around a track, overtaking other cars and taking corners at speed. Then the second example, the third example, they're asking with one of these I can what. So as you can observe from these examples, like they are asking like a lot of open-ended um, questions as well, and the model is basically completing it uh, with appropriate and exact, you can say exact answer to that image. So the here they are not really here they are not really training any of the language models. They're only training the vision encoder, which I'll be talking ahead in this paper. And using that vision encoder, they are trying to see like what is being prompted and what is not being prompted. So that's the high level summary of this paper. um, so these author, they first start by start by introducing like how language models are really popular these days. So they use some auto-regressive transformers, for example, attention models or some and other models like that. And they say that they have shown impressive performance for natural language processing, and so they are also called like few shot learners. I've attached this paper, which is language models are few shot learners, which is again a paper by OpenAI, and I think that it was published last year itself. So these models, they have shown a rapidly like that they rapidly adapt to new tasks and styles of generation, which is only by prompting. Like for example, if I have to switch from a formal to informal language, like for and examples which was shown in the previous slide. So they can learn to perform a new task from a few examples without great change, great gradient updates. So that's why it's called like the few shot learners. And few things which are really impressive in this is that they have a retrieval. They can retrieve relevant encyclopedic or any general knowledge when given a relevant context. For example, if I have to answer the question such as what's the weather like today, when did the French Revolution begin, etc., etc. So, and another thing is that they can use new words in appropriate ways straight after being taught what those words mean. So this thing is called the fast binding. the process is called fast binding, where you can just give like few examples, which is like just known or new examples, and they can use it in a very appropriate manner. But these large scale languages, they are really blind to the modalities other than text, and they don't really know how to communicate with any visual representation, and that's the gap that they're trying to fill here. So they introduced something called Frozen. So Frozen is nothing but basically they are just freezing the pre-trained models, which for the language models, and say for the self-attention layers and for the text embedders, and they're only trying to train the vision encoder. But I'll show it in the next slide. So the Frozen basically it consists of a neural network which is trained to encode the images into the word embedding space of a large pre-trained model, such that the language model generates a caption for those images. So in this paper, they have used a GPT-2, but you can use any language model. In this case, you can also use GPT-3 or anything which is available right now, because this is, I think, last year's paper. So I mean, till then, a lot of new papers have come into picture, and which are performing really good. And I'll talk about that later as well. So the weights of these language models are kept frozen, but the gradients are backpropagated through the language model in order to train the image encoder from scratch. And they are performing really trivial baselines of a wide range of tasks without even seeing the training examples before the for the benchmarks. Now the authors have also mentioned that the goal in developing this frozen model was not to maximize the performance on any specific task, and it's not for the I mean, they are not basically trying to match it with the state of the art models. It's just for experimentation and for for showing that how you can just fill those gaps between the language model and the vision encoder using effective methods. So yeah, going ahead. So this is the example which can be more clear. So basically, they have this whole model where they have the language model and they have the text embedder language model, and both of the for both of these language models, the weights are frozen, and the gradients and the weights are only changed by which is going through this language model, and it is basically changing the weights of this vision encoder. So this vision encoder is nothing but convolution layer network, which will be telling you like what does that, which will be giving you the context of that image. Now, I found, I mean, I really feel like this should be changed a bit, because like, for example, in this whole context, it should start from like start of sentence, and then this arrow should come here, and then this arrow should come here, because then it should be telling us that from where the sentence is basically starting. And so here, as you can see, I mean, that's just my observation. So as here you can see that for this particular image is basically giving a caption of or description of a small red board, and then in the next one it's going to predict what is going to be the next word on the water. So it's not going to give the exact, I mean, it's not going to give the exact image caption for that language model, else it will be just like copying from one language model to another language model. That is not what's happening. So they will start from the start of the sentence here, and then it after start of the sentence, it will be basically predicting which is the next word which is going to be, or which is the best sentence which is going to generalize or describe this image which is there. If you guys have any questions, just let me know. So this thing I've taken straight from the paper itself. So they basically exhibit a strong zero-shot performance on multimodal tasks, and that has not been trained on. So okay, just to give like a context. So these images are not being, I mean, they are not being trained on these images at all. It's basically just a vision encoder, and the way it works is they are okay. So a very important point which I didn't tell. is that they're basically trying to encode these images as the vector embeddings, which are the exact dimension for this language model, so that there's a consistency between the the layers for the dimension between this vision encoder and the language model for which they are outputting or giving predictions. So yeah, that's one point which is like really important. So yeah, so they found like it is it's performing really good on these images which is not being trained on, and they are giving good performance on the task like visual question answering, and even it also performs really good if a context or some context is given for that image. Like for example, in this previous in this example itself, if I ask a question, what color is the board, then it will be giving or what is there on the, let's say, on near the water, on the water, so it will be giving me like there's a small red boat on the water, something like that. So a context, if it's given, then it performs really good. If it's not given, then there's another case where the context is not given and it will just perform, it won't perform blindly, but it will just perform like an image caption model, which is which is a very general case in most of the tasks. So the frozen in the system is genuinely just open-ended and unconstrained linguistic interpretation of images that often produces compelling output. That's like the main twist of this whole paper, because they are not really trying to map. So they're trying to find a way in which you can ask open-ended questions, like in this example as like which with one of these I can do what. That's like an open-ended question, and they've only given the image of a screwdriver here. Yeah, only a screwdriver here. So that's like a very open-ended question, and that's what the model is trying to complete the whole task which has been given. So to back up a little bit, this research is inspired by the success of prompting. So prompting was shown as it is shown here. It was shown during the GPT-3 paper, and it is where you add this context to the input to guide the generation. So for example, you're given this title and you're given the subtitle, and you're asking this model to complete the you're prompting this model to complete the whole paragraph, and this is the paragraph that's been generated by the model itself. So prompting generally refers to adding the additional things in the input to guide the language model, and then so that we can see. In this case, we can see the multimodal language modeling as for performing a visual task as well. So that so the main inspiration for this was to give the context in order to use the success of the prompting, which is done in the previous papers. So coming to the architectures in this one, any questions till here? If you guys have any questions, just let me know. Cool. So to talk about the architecture of this paper, basically the architecture is all dependent on the language model which I showed you here, on the model which I showed you here. So so yeah, they have like two language models which are frozen here, and they present. So they train the image, they train the model to caption these kind of images, and so that and then they also provide a captioning data set, which is the C4 data set, which I'll be talking in the next slide. So they use something called conceptual captioning, in which given an image, they will basically produce a caption which is going to be much more meaningful according to the image. And given a prefix of the context, it basically trains by using that image, that vision encoder, and that is just been, as I told before, it's basically not a very complicated model. They're just giving the prefix of the content, and it's been trained by using the convolution networks. And after presenting the image as it were the sequence of the embedding of the text content. So as I told before, they're basically presenting the image as if it were the sequence of the embedding, so that they can map the so that they can map the so that they can map the language model and the vision encoder both in order for them to have the consistent dimensions. So that's it's the crisp of the whole model. But and what they're trying to do is they're trying this model has been trained on 7 billion a model which is of 7 billion parameters on C4 dataset, which is like an open source dataset with a maximum likelihood objective. So this is basically, it's just like the self-attention model, that like how a self-attention model works. And when we try to treat few shot learning with language model, we try to treat them as a text in and text out interface. Like for example, the input that you're giving into that text in text out interface is going to be the prompt in this case, and the output is we want it to conceptually give us as an output. And on the middle, in the middle one, it's basically text tokens are transformed by, it's just exactly what I told before. So this visual prefix and this vision encoder is explaining just that. So you're basically literally mapping the whole vision encoder output to the dimension of d into n, and reshaping the results as a sequence of n embeddings with each dimensionality d. It's just basically mapping each and every vision encoder and in the language model. Exactly same thing which I told in the previous slides. So, okay, in this case, okay, so in the language model, basically what happens is that you try to do it as text in, text out, right? But in this case, what they're trying to do is they're trying to do something called vector input, vector in, and text out. So that's the only difference between this paper and the paper which was there for GPT-3 or any language model which is there. Because we are taking this vector input because we don't really know if the input that we are getting is going to be an image or a text. Or in other words, we are trying to map the images to the text embedding layer. So that's why we need to transform it to a vector representation, or both of them in the same latent space in order for us to give a proper prediction. Okay. So without any further training, what these authors are claiming that it's not best thing to do. It's not the best thing to do any fine tuning, and they're also claiming that it's better. Sorry. The fine tuning is much better than the pre-training because there's a huge asymmetry in the size of the caption dataset and the language dataset. Basically, because I mean, that makes more sense because the conceptual captioning, basically you are having all the data sets which are handmade or which are done by human supervision, but the language data set is basically all the text or all the embeddings or all the words which are present in internet. So that's going to be much larger than the caption data set anyway. So that's why it's better to fine tune it rather than pre-training it. And in the result section also they have mentioned that if you pre-train it, the results or the accuracy will basically go down. And for the fine tuning or just freezing it makes it much better because you don't have to do anything. So all the training was done on the conceptual captioning, and it has an interesting property that all the named entity in that data set was removed. So if you have the data set, like for example, this is a lion or this is a dog. So the name entity was removed. Basically, you don't have any information on whether that object is a dog or is a lion or is a car, airplane, anything. So all of those things were removed, and I'll be talking about that in the upcoming slides as well. So that means that they don't have to teach the model about the name entities by captioning tasks. So that has already been done by the language model, which has already been pre-trained on that large C4, I mean that 4 billion, 7 billion parameter data set that they already have. So that's a very interesting thing which I found here. So as I told before, they are basically maximizing the likelihood of the embedding for the relevant text and for the number of tokens in caption dataset. So in this case, the I is the visual prefix and the T is the caption of that image which is being presented. and they want to give the output y, which is the output for that. What's the context of that image with respect to the image that we have? So that's the I mean that's the likelihood, that's the likelihood that they're trying to maximize. And while the parameter p, this one p theta, is are frozen, each element I, in this case the visual prefix of the receives a gradient from this whole function, enabling the parameters of the visual encoder to be optimized with the with the sum, I mean, with the same backpropagation, we using a very normal optimization algorithm, like let's say stochastic gradient descent or something like that. And they try to use a relative positional encoding. So that enables the transformer to generalize to prompt sequences where an image is not always in the first absolute position, and like where more than one image can be present in that context. So what I'm trying to say is, in an image, for example, I think this is like a very basic thing. If you have like this is like a human being and you have like a car here, so I mean, I can have multiple objects in just same image. So they're trying to use a positional encoding so that for this image, for this object, and for this object, they have a particular encoded information. And then I can prompt whatever I want to prompt, and I can ask whatever questions I can ask. And then that question will basically be that question, or whatever I'm asking is going to attack the embedding or the position on which I'm basically asking the question for. So for example, if I'm asking where in this image is a human being, then that prompt will basically go to that position of that human being, and then it will be giving me that context or that output for that image. Does that make sense? So coming to the inferences for this image, basically, so they're trying to show in this example, they're trying to show like how if you give like more context to the image or more context to the model, at that time you can see that you will be getting a much better prediction. So in this case, let's say you have like just one image, which is this is a car, and the question that's been asked is what color is the car. So the answer for this self-attention layer will be blue. But in the next case, for one shot outside knowledge, basically, if you have an image and it's asking who invented this, and the answer that you are giving is the Wright brothers, and in the next one, you're just giving this image of this iPhone, and you're saying who invented this. So as you can see here, when I'm giving this context, it's basically telling that I need to take the context of from the language model about who invented what, and then I'll be giving that output to that using that attention layers. Now, a very interesting point that the authors have done is, as I told before, that they have removed all the named entities, correct? So let's say I have given this image, which is of an apple, and I'm giving that this is a DAX. I know that this is an apple, but I'm giving the model as this is a DAX. And for orange, I'm just replacing that orange as a blicket. So this is basically used for few shot image classification, where I don't have to give the relevant class or relevant class for that object, and it will basically give me the answer for the prompt that I'm giving. So in this case, what is this? In this image, it will just give me an output that this is a DAX. So they are removing all the named entities, and whatever prompt that you're giving, it's going to act according to that. Now, there's a very interesting case which I'll be covering in this next slide. So just to give a context, the model basically decodes the output sequences greedily, and then these outputs are compared against the ground truth answers of the task following the normalization technique. And also the classification in this one is basically they're just trying to use this self-attention layer, and then they're basically adding a softmax layer in order for us to get the prediction for the best class. So in this one, basically so they have given like two examples on which they're trying to prove the baseline of the experiments that they've done. So for first, they're using the mini ImageNet, and the second is the fast VQA. In this, so they have like two images here, two you can say two inner shots in this one. So we know that this is a lion and this is a husky. Again, a lion and a husky, and they are basically giving me a context that this is a blicket, this is a dax, this is a blicket, this is a dax, and then they're going to give the question of the ImageNet, like what is this. So the model will be completing it as the blicket. Now this is what we have been seeing in the previous examples as well. Now, a very important part in this is that this example is being rendered by the task induction part here. So you can see that I want the task. I'm giving it the task that I want the answers with DAX or Blicket, and only in that context I will be getting that output. So but in the second one, which is a very interesting case, is that you've been given this is a blicket, this is a desk, and you're basically been given a vase and a wooden table. But the question for which I'm going to ask here is, what is the DAX made of? Which is a very open-ended question in this case, because I'm not giving any information in this fast VQA about what is it made of, or any other information which is relevant to the material of that image. But you can see that the model is basically giving me an output of wood. So what is this made, or what is DAX made of? It's made of wood. So that's a very interesting case in this case, where I'm not even giving the context, but even though I'm not giving the context, it's giving me a very I mean, it's giving me the correct comparison or completion of that output. And so this fast VQA is the new benchmark for this paper, where they're trying to show for a given image, basically if it's going to create a appropriate output or not. Okay. So they're given. So for the given experiments, basically we are all we have seen is that they are giving an image, and then they are basically trying to use the language models and giving the output for that. But what they have also mentioned, that the strength of this pre-trained language model is a double-edged sword. So they have observed that even if you do not give that image for that for this output, or for you to create the output, basically it's still performing really well, even if you do not give the image but only give the context. So in the previous example, if I just give the context of if I do not give the image, but I just give the just give the context, let's say like this one, yeah, who invented this, and the Wright brothers, and then the next question will be who invented this. And so it will give me some random object, but it will be giving me some it will be giving me something which is relevant to that object. So let's say if I just ask who invented a mobile phone or iPhone, it will be giving me Steve Jobs anyway, without even looking at the image. So that's the so they saw that this is basically a very interesting case. And it's not an interesting case, it's basically the baseline which any large language model provides you. So what they try to do is they try to do two things. First, they are giving the image and the language model, and the second, they are just masking the image and just giving the caption, which they're calling the blind baselines of these images. Uh, Even though they're giving this blind baselines, you can see they have not given the exact results in the paper, but what they're saying is that it sometimes it outperforms the blind baselines, which also inherits the few shot learning abilities of the language model. But they're actually performing really well if you look at their presentation. You can see that there's basically comparable you know results for even the blind baseline and for the given baseline which they have. So as I told before, they are basically giving them the model. They're basically giving the prompt and the image, and they're giving the context of it, and it's basically giving a proper output of it. Now, when I so an example about them removing a named entity is this one. So let's say if I do not give any context in this, and I just give the context like who this was invented by, or what this object is, it will give me output like this is an airplane with something something. And so they've also shown that this will give me an output with some garbage value as well, some garbage sentences as well, like complete, or this is an airplane, full stop, and then it will give me some garbage some sentences. But if I give the context about what that object is, like if I write that context, that it will be giving me the proper output of that object, or telling what that object is. So that's the experiment that they try to do, and they haven't really shown the results of this in the paper, but they have told that in the paper itself. This is the interesting case where I found, I mean, that I found is they are not giving multiple images, but only the context and only the image and the question for which they want, which is a very open-ended question. So in this image, you can see that there's a vine which is spilled on the carpet, and here the question is, I have this problem, what can I do? And the model completion is, if you can remove it, gently rub the scuff with the clean white cloth, and end of sentence, which is very impressive because I'm not giving anything else. I'm just giving this image and that question. And there are no multiple, there are no multiple images for it to compare or check like what is the background of that image and what needs to be done. So this is a really impressive example which I found. And I mean, yeah, so coming to the results of this, so so as I mentioned, and not I, as the authors mentioned, that they're not basically trying to compare to any state of the art results. They're just trying to experiment with it, just trying to fill the gap between the language model and the vision encoder. So as you can see, this is the actual Oscar is the baseline which they are taking, and it's basically performing really well, 73%. But Frozen as a whole, it's not really performing that well. So n equals 0 is 0 shot, n equals to 1 is 1 shot, and 4 equals to 4 shot. So they're not really performing well. I mean, not that well using just this Frozen means that we are freezing the language models and then giving that output. So you can see it's 29.5 and 35.7, which is not that good. But the main point about this is that so this Oscar is basically, it's not a few shot learning model. So you don't have a multiple shot in this case. It's just like one shot or 0 shot, and that's what they've been using. And so also another thing which is really relevant is that if you train the whole thing from scratch, if you train the whole language model and the vision encoder from scratch, is basically giving like zero accuracy or zero in this case. And when you fine tune it, even when you fine tune it, it's basically reducing the performance. But when you train the blind oh yeah, this is the blind result which is there. So when you mask the images and only give the context, you can see that 29.5 and 26.2 is basically it's comparable, but it's still lower, but still comparable. So yeah, these are the results that they are showing. So the second result is basically the task induction. So task induction means that in this case, like so for whatever task that you're giving in this one, if you're giving the task, mentioning the task in that mod, in that in that prompt, and then you want the output, it's basically in the result section you can see, yeah, sorry. So in the result section you can see that the task induction performs better than without the task. So, and the real name is basically the mini ImageNet data set that they are using in order to, yeah, mini ImageNet data set which they're using in order to check if that if it performs better in that data set or not. So these are the, yeah, so these are the results and the explanation of that paper. It's not a very complicated paper as well, and it's basically just saying the same thing all along the paper, that they're basically freezing the language models, and they're only training the vision encoder, and that's all that's been there. But what I find is that it has a strong generalization. And so few multimodal tasks, both 0 shot and few shot, with completely open ended generalization, generative text output. So yeah, that's a very impressive thing that they have done. So even for a very open ended question, it performs really well. Just after I think 2 or 3 days after this paper was published, there was another paper which is CLIP. That's learning transferable vision visual models from natural language supervision. This CLIP model is basically an opposite has an opposite working of this paper. So there you'll be giving the textual context, and it will be generating that image for you. So and and this clip is a really famous paper, I think, and I think DALI Mini is being trained on this clip dataset or clip model. So this was the overall good experimental paper, but I think even the authors have mentioned that this is far. I mean, they are not really trying to compete with any state-of-the-art models, but only trying to experiment with this, like how you can fill the gap, and that's all. But it's really impressive that they found answers for open-ended questions, even though you do not have a lot of context just by looking at that image. So yeah, and that's all. I conclude the paper. Do you guys have any questions here? Okay, if no one has a question, then I'll just close.
I had a question. I was wondering, they show these really impressive, like open-ended generative text outputs, but at the same time, the performance seems to be like much lower than the Oscar paper. Is it a question of misaligned evaluation metrics or something? Because what I don't understand is, like, it seems really impressive, the examples you gave, but then at the same time, it seems to perform much worse than the Oscar model.
Yeah, so as much as I read, I think the Oscar model basically that's another language model itself. They are not really trying to have any vision encoder in that one. So another thing is the comparison between this Oscar, the baseline model, and the one that they have provided is not that relevant in this case. That's what I found, because Oscar is only been trained on language models, but not entirely on vision. And also, yeah.
Do they do VQA? Like, what does Oscar evaluate on?
I'm not really sure. I didn't read that on what Oscar evaluates on, because in this case, I think, yeah, I'm not sure. I'm not sure. I didn't look into that.
Because I was wondering, it seems like it's doing really well, but then the end shot accuracy seems to be low compared to other models, which I was like, which is interesting, I think, because maybe then also the evaluation metric that they compare to. I understand that they're not even trying to compare to other models, so it's not super relevant. But I was just like more surprised by the fact that when they do compare it, it seems so much lower. So I was thinking maybe the metric with which they like evaluate is maybe a little bit misaligned with their actual goal. Because let's say the example you gave, right, with the wine, maybe the official, like, correct thing to say would not be this sentence, even though for us it seems very natural, at least, right?
Yeah, I mean, if you're looking at the output for this, I think it's more as how we can compare it to the human response as well. Even though it's like a random thing in this example. I mean, yeah, you can have any image in this case, and if you have the same output, then it doesn't make sense. So what I feel is why the evaluation metric, or why the results in this case is lower, is because in Oscar they haven't really removed anything, any named entity or anything like that. They're giving the full information to the model, but in Frozen they're basically they're removing the information, and then they are trying to train or give the output, which I think even the authors, they have mentioned that because of that reason, I think there's like some disturbance or some inconsistency between the results. But I'm not really sure what metrics they're using in Oscar dataset or Oscar model. Sorry.
Yeah, no, I think it's pretty cool, but it seems like their quantitative results are like a little, it's hard to quantify how good it's doing. It seems like that. In terms of like, like with quantitative numbers, like it's hard to quantify how.
Right.
done.
Right. Probably, but again, I mean, if you look at this, the second one, which is like if they train the whole thing from scratch, is basically zero
Yeah,
for anything. So that
Yeah.
that doesn't that I don't know like for what all information that they're taking in order for them to train it from scratch, so that they're getting this output as zero.
yeah, it's
So that's
also cool
really,
that they can do just like frozen. Seems to perform better without training it than
yeah.
with.
So that's like, and they have not really given in much information on why that's happening in the paper as well. So yeah, I mean, again, it's just they're just trying to give like a concept of this model on how it works, but they haven't really. I don't know, because they have not really mentioned in the paper like uh, how they're trying to improve it. So
I do think it's good to do this more, I guess, a little bit more fundamental work to look at why these models work well,
yeah,
or how they work. Although, like they're saying, if they don't mention too much about the actual reason why, that may have been, that I think that's probably important future work into looking at like why this happens.
So a very interesting thing which I found is that in this clip paper, that they have cited this paper itself, and here they are basically saying that we have done the exact opposite thing of what we are mentioning in this paper, the multimodal paper. So now when I look at the clip paper, they're basically using a lot of new metrics, but then the whole thing it changes because they are basically evaluating on the image or on the language model first, and then checking if that image that's been given as output is correct or not. So yeah, it's like the whole complete chain itself in this paper.
Hmm.
Yeah. Any other questions? Cool. So I'll just stop the recording and